the Arctic was warm. For example, if we go back, say 3 or 4 million years ago, the Arctic was forested. We had no Greenland ice sheet. The Arctic was very different. We had no sea ice. And then gradually over time, the climate cooled, and we started to go into the major ice ages to get to the climate we have today. So the Arctic that we have today is a system that operates on both short time scales and for many people we're looking at changes in the weather. But if we average weather patterns over longer periods of time, we start to look at climate change. So I'm interested in how the climate has changed in the past and how that compares to what's happening today. So I think if you don't remember anything else from many of our comments today, is that the Arctic matters because what happens in the Arctic doesn't stay in the Arctic, and what happens at the lower latitudes doesn't stay in the lower latitudes at all. We know that over the past few million years with glacial and interglacial cycles, the Earth's atmosphere has had a composition of carbon dioxide and greenhouse gases, and I'll use just carbon dioxide, for example, that oscillates between about 180, 280, 180, 280 parts per mil. So I like to liken that. Some people like to think about maybe their cholesterol level. They keep track of that. Well, you just think that there's a normal range in which the Earth operates within a range of 180, 280, 180, 280. But today, we're now in a different world where globally we have carbon dioxide in the atmosphere well over 400 parts per million. So there's nothing normal about that in the last few million years. And so this has important consequences. And just to put that in perspective, there's two main ways we as geologists, I'm a geoscientist, two main ways that we look at the Earth as a system and how you can warm the world globally. One way you do it is you change the way the Earth orbits the sun, and on very long, thousands of year timescales. But the other way you do it is you change the atmospheric composition, and that's what humans have done. We're now entering a time, an atmospheric composition that we have not seen in over 3 to 4 million years. So this has really important consequences, primarily particularly because the rate it's happening is faster than we've ever seen in geologic history that we have the capacity to measure. And so this is really important. So one of the first slides I have on the screen is particularly a image of the Greenland ice sheet, and it shows in very bright red those areas of the Greenland ice sheet which in the last few decades have lost incredible amounts of mass, so that the ice sheet is actually melting and delivering that ice from land into the sea. And of course that has consequences for rising sea level. If we go to the next slide, please. The next slide shows you not the Arctic, but in fact the Antarctic. And what's happening there is scientists studying particularly the West Antarctic ice sheet, which is basically these, well, let me explain. In this diagram, the red areas are floating ice shelves around the Antarctic ice sheet. Now these ice shelves are quite thick, hundreds of meters thick, but they're floating on sea level. And they act like buttresses. So on the left-hand side of the slide that you'll see there, you'll see a cathedral with arches, these buttresses that hold that cathedral up. And I want you to think about these ice shelves like the buttresses on a cathedral. If you remove the buttresses, the cathedrals fall down, and that was what early architectural design was using. We have to think about these ice shelves are in fact the buttressing system of these ice shelves. And in the West Antarctic ice sheet, we now are seeing Thwaites Glacier, Pine Glacier, and other areas undergoing massive retreat, and in a way that the glaciologists are arguing it's really unstoppable. There's no way for us to turn that mechanism off. So we have both Greenland melting quite a bit, and we have Antarctica melting at an unstoppable rate. And scientists in both areas, studying both Greenland and Antarctica, are trying to understand the mechanisms and how fast and what we can say about sea level rise. So if we go to the next slide, this slide is from the Intergovernmental Panel on Climate Change, their most recent assessment. And this RCP values are representative concentration pathways, which talk about CO2 scenarios. So just to just think about that red line that says 8.5. That's the worst case, business as usual. We're going to just keep burning fossil fuels into the future without any change in that rate. So that line shows you the increase in CO2, and we're pretty much tracking on that right now. The best case scenario is the 2.6 scenario, the little green line below, which has to do with forecasting a massive change in the way we burn fossil fuels and use them for energy. So on those two pathways, you can see 2.6 is certainly a best case scenario that we would hope for, that may be coming out of the Paris agreements. And business as usual is this red line. So if we go to the next slide, this kind of captures a lot of what I'm concerned about the future, is that what's happening in Greenland and what's happening in Antarctica is causing sea level to rise. And this diagram shows you the recent changes in sea level. It points to where we are today on those curves, and then shows you the business as usual and then the best case scenario in terms of sea level rise. And you can see that even in the best case scenario, we are already committed to a lot of sea level rise, perhaps as much, in a conservative person would say, maybe as much as a meter, and that's probably a minimum, conservative minimum. It may be worse than that in terms of global sea level rise. And so that has serious implications for coastal cities. And I just want to say for a minute here that one thing that's really hard to understand, and you can ask me questions about this, but it turns out that because of the physics of the Earth and the gravitational pull, it turns out the melting in Antarctica is a worst case scenario for Alaska. And sea level would go up, say, a meter globally. It's actually going to be another 10 or 15% worse than that in parts of Alaska and the east coast of the United States because of certain aspects of gravitational pull on the Earth's surface and on sea level. So this, again, has very serious consequences for sea level. And of course, the other thing happening with this changes in carbon dioxide, now well over 400 parts per mil. And I want to mention, I think when I was born, 1955, the CO2 was only at 310, and it's accelerated quite a bit. So we're accelerating the rate of CO2 faster now than ever before. So this has the warming of the Arctic has serious consequences also for sea ice. Sea ice is now at a record minimum, particularly for this winter. It's at a real record minimum, and that has big consequences for changing the albedo or reflectivity of the high latitudes. So if we go to the next slide, please. I'd really like to focus on the sea level issue. This diagram, and you may have to click, okay, stay with that right there. This diagram shows on the vertical axis changes in sea level, and then across the top, it shows you changes in CO2 over time. So the first dot that's way down there low at around 125 meters below sea level, this is where we were at during the last ice age. So that shows you where sea level was and what carbon dioxide was at about 180 parts per mil. If we come up that curve, we come up to warmer periods of time when sea level was higher and CO2, carbon dioxide in the atmosphere, was higher. And this is based on geologic information. And if you click the next one here, please, and the next one. Can't see if that's coming on or not. So you should see a band between 0 and 25 meters above sea level that shows on there. And that is where we have a lot of our infrastructure, where people are living around coastal cities. So even though a global sea level rise of 1 meter is what is projected by the IPCC, the actual absolute level of the sea will change depending on where you are on the planet. So we can identify as geologists certain parts of even our United States where sea level rise will be worse than other places. For example, New Orleans, the Gulf of Mexico is geologically sinking anyway, but then you have a much larger range of sea level that's rising there. And again, if we go to the next slide, this is just to emphasize that we have a tremendous number of people living within a meter or two of sea level, or even within a couple of meters of sea level. And this has pretty serious consequences for all of the infrastructure, the cities and towns, not to mention Think of Miami, Florida. I mean, the Florida Keys are going to be toast, okay? So the sea level rise, we're already committed to probably at least a meter of global sea level rise. And this is within the Paris Agreement. We're talking about trying to limit CO2 emissions so temperature only rises, say, 2 degrees. The problem is we're already at about 1 degree of warming on the planet. So we've only got 1 more degree to go. But the thing is, probably not going to stop at 2 degrees. So we've really got to worry about going to alternate energies and dealing with our fossil fuel issues. And it's a particularly difficult issue for economies like Russia or even the economy of Alaska to make that commitment and look at the consequences of that. So I would like to communicate that we're concerned about the climate and how it's changing so rapidly. We're concerned about the rate at which it's happening, but we have solutions that we can move to, which will provide opportunities for us to turn this around a bit. And I think that it's really important that we consider those opportunities and take on these as solutions for alternate energies, despite both the political and economic difficulties that may cause us. So with that, I'll stop there. Thank you.
All right, thank you, Julie.
Our next speaker is James Overland. He studies scientific support for decision makers on climate change and ecosystems in the Arctic and subarctic for NOAA. Thanks, James.
Thank you. Yeah, good morning, everyone. I'm going to address the topic of whether these changes that we see in the Arctic will impact the weather and severe events in mid-latitudes where most people live. And we already are seeing very large changes in the Arctic in terms of temperature and loss of most of the volume of sea ice already. So the question of whether the Arctic impacts mid-latitudes is no longer a question of if there's a connection, but how large that connection will be and whether it's going to be localized in certain areas. So we can go into a bit of the physics of what's important about this problem. And on the slide here, I have 2 pictures of the jet stream. You're basically looking down at the north, from a view of the North Pole, and we're looking at the jet stream at 2 different times. And the jet stream is a region of strong winds that blow mostly from west to east. And on the left-hand side, sometimes you see this very symmetric circular or elliptical jet stream, and that tends to bottle up all the cold air in the Arctic north of the jet stream. And so that's a case where the Arctic and the mid-latitudes tend to be separate. But the jet stream can randomly shift from this more symmetric circular pattern to more of a wavy pattern that's shown on the right. And in the wavy pattern, if you look at it, there's certain areas where the winds are coming out of the south and they can bring warm air up into the Arctic, and other places where the winds then are blowing out of the north and they're carrying colder Arctic temperature into the southern region. And in the last 5 years, we're seeing a lot of this wavy pattern. for those in Alaska, you're on the warm branch. So last winter, the last two winters have been particularly warm. And then if you follow the wave around the Earth, there's a tendency for the cold air to dip down into eastern North America, and we have snow reaching Georgia and Florida and so forth. And Eastern Asia is another place where we tend to have the cold air reach down into Eastern Asia. And the atmosphere tends to flip on its own from this more circular pattern to the more wavy pattern. But when we do have the wavy pattern occurring, the warmer Arctic, especially in places where we've lost sea ice in the summer and then continue to have thinner ice into Europe, if those places are near where the jet stream waves are, it can help prolong that wavy event. And there's already evidence to show that we're starting to see that happen. And with the continued warming of the Arctic over the next 2 decades, we expect that condition to increase, where we'll have more impact. One positive thing of that is with the warming of the Arctic continuing, we hope that we can use this to improve weekly, monthly weather forecast, because the wavy pattern would have a part of the Arctic reinforcing it. Next slide. So, one example of these cold events, here's Boston last year digging out of the snow, and most of the connections occur when we have this wavy pattern. And so the wavy pattern can last for a week or two. So rather than thinking about cold winters for 3 or 4 months, we're thinking that the connection with the Arctic will be more when we have the occurrence of the wavy patterns that get reinforced by the Arctic. So they're going to be more on the weather event scale of 1 to 2 weeks rather than a seasonal change. So in summary, there's evidence that it's not a question of if the Arctic will influence mid-latitude, but just how big that effect is. And we know for certain that over the next 2 decades that connection between the Arctic and mid-latitudes will increase. Thank you.
Thank you, James.
Our next speaker is Bhatt. She is a professor and chair of the Department of Atmospheric Sciences at the University of Alaska Fairbanks College of Natural Sciences and Mathematics and the Geophysical Institute.
Thank you. Over the last decade, as the Arctic has warmed, tundra vegetation has become greener. But if we look at the trends over just the last decade, tundra vegetation productivity has actually been declining. We monitor tundra vegetation using long-term data sets from satellites that began in 1982. And the satellite data is used to construct this index called the NDVI. So think of it as a vegetation index. The bigger the value, the greener or more abundant the plants. And now if we split up the two periods of our full record into the early period and the later period, the trends on the left-hand side are really green. Greening means the vegetation's greening and becoming more abundant. But if we look at the trends over the most recent period, we actually see greening, but we see bits of browning or declines in vegetation since about 2000. So what is causing this? It's kind of a conundrum. What we find is that the declines in vegetation over the last decade have occurred during springtime. So that means that the early season has somehow been declining. And some of our data analysis suggests that it's due to increased snow. If there's more snow, this is the high Arctic. If there's more snow there in spring, then the plants green up later. That's one mechanism, but more than likely there's probably multiple things going on because the Arctic's very heterogeneous. There's lots of different things going on. Another thing that we know happened is in the summer of 2015, there was a very early snowmelt on the north slope of Alaska, and then the plants greened up. The first picture I had on my slides was of the blueberries, and then cold weather came because it was still winter, and those plants died. They browned, and they stayed dead the whole summer. So in certain areas, that might be the mechanism. From talking to elders in the Yukon-Kuskokwim Delta, we've been, where there's been browning over the long period, they suggest that there's been less water available for the plants. So they've noticed that berry crops have been weaker. So again, each of these different areas have slightly different mechanisms, but they're all consistent with a changing, warmer climate. And at the bottom there, I'm showing a plot of the NDVI index, the vegetation index, over the whole record for the whole Arctic, and there's a lot of up and down. And you can see that since about the mid-2000s, it's actually been declining. Now, when I add 2015, we'll probably get a slightly different answer, but there's lots of ups and downs, and what we really need to understand is what happens from one year to the next, because that's where it has an immediate impact on people's lives. The overall basic science is that when sea ice retreats, it moves away from the coastline, and the tundra is a narrow strip of land right along the coast. The tundra can warm up when that ice goes away earlier, and that's what we've seen happen over the full record. But when the sea ice moves away from the coast during the summertime, the land warms up, and then the tundra vegetation has more warmth available, so it can become more abundant. But what we think's happened as the sea ice is declining earlier and earlier, we actually have much more open water right along the coast, and that's probably increasing available moisture, increasing cloudiness. So that could be affecting the productivity also. So again, the climate's a very complex system, and we as climate scientists try to dissect what's going on and understand the pieces. So again, it's not a simple answer. The simple answer is it has greened, but there's variations locally. Now, how does this, potentially affect the globe? First, the simplest arguments are when you have more vegetation, the vegetation has a lower albedo than bare ground, so it can absorb more solar radiation, and it contributes to a warmer Arctic. And we've already talked about the effects of the warmer Arctic on the larger scale climate. As the vegetation changes, it also alters wildlife habitat. Birds don't know borders. They travel from Mexico to Alaska, and if their habitat changes, that affects, global ecosystems. Similarly, though I didn't talk about it, the productivity in the ocean has been shifting, so that shifts the migration of whales, or where fisheries will be at their maximum or most abundant. Another final thing I want to mention is that June snow cover has really declined in the Arctic. And that has really important consequences for forest fires. And this is not something I showed you data on, but earlier snow melt will give us a longer potential fire season in the Arctic. And we know that when we have large areas of the boreal forest that burns, that contributes carbon dioxide to the global carbon dioxide budget, but it also sends pollution to the lower 48. We had satellite pictures last summer of bad air quality in Wisconsin due to fires in Alaska and Canada. Again, year-to-year variability is what really matters to people, and that's where it has its most immediate impact. And I guess I would make a ploy for, we couldn't have done any of this research if there hadn't been consistent long-term data sets. So we really need to make sure we continue with sustained Arctic observing so we can understand what goes on, both to understand what's going to happen next year and what's going to happen 20 years from now. Thank you.
Thank you. We'll be taking questions for the panelists now. Again, if you are submitting a question on the webcast, please make sure you identify yourself and your outlet. And if your question's for a panelist, please note that as well. Are there any questions?
Thanks. Matt Miller from KTLO in Juneau. Just a general question to any of the three panelists there. What's your view of the current, one of the theories, that the loss of Arctic and Bering Sea ice is contributing to the lack of cooling into the Northeast Pacific and also the Gulf of Alaska, and altering and manipulating the surface fluxes in the ocean? And I also have a follow-up to that.
Well, as you know, the Bering Sea has been cold for the last 6 years up until 2 years ago, and then it's been warmer again. And we think that the southern Bering Sea is tied more to what's happening in the weather in the North Pacific, and the North Pacific has turned warm again after a cold period. So what we're seeing now is the warming of the North Pacific, we think, is enhancing the warming in the Bering Sea. So we've reversed the cold period in the southern Bering Sea, but then that air is continuing even further north, so the Arctic warming is even faster due to the air coming up from the Pacific. So it's part of this wavy pattern that once you're warmer in the Pacific, it helps set the jet stream coming from the south to the north, and that's carrying warm water. And we've had 2 years of this condition, so we're probably, based on what we've seen before, we're probably into another couple years of warming before we shift back.
My question was in reference specifically to the warm water anomaly, otherwise known as the blob. And so I was kind of curious as far as whether the loss of Arctic sea ice was contributing to the lack of cooling in the Northeast Pacific and the Gulf of Alaska. And my follow-up was, and you kind of alluded to that, what kind of effect is the warm water anomaly? How much is it contributing to the further alteration of the jet stream?
A lot. The Pacific's been warming for the last 5 years, but the maximum heat temperature region is moved around a bit. So a couple of years ago, we said, well, there's a blob in the central North Pacific, and then in the last year, the warm sea temperatures have been closer to Alaska, which we would call more the Pacific decadal oscillation that's turned warm in the Northeast Alaska. So what I see is this shift in the Pacific is actually shifting what's happening further north. We've had a real minimum ice year because we've been pumping all this warm air back in, and so the warm air over the North Pacific helps reinforce that southerly and northerly flow, and the lack of ice in the Bering Sea will warm up. We'll have a warmer spring and probably summer, and that helps reinforce that flow from the south. So I'm before we were thinking, well, most of the change is going on in the Arctic and it's leaking out. Well, now it's going both ways, both in the Pacific that you're alluding to, and we were just talking earlier this winter, the jet stream went all the way from Spain up to the North Pole, and we had almost melting temperatures in the at the North Pole, which was just unheard of. So now we're seeing this more wavy pattern. If you want to go even more out there, you say, well, maybe all the extra heat in the Arctic is making this wavy pattern more unstable and larger, and it's having effect all the way around the Arctic.
Can I squeeze in one more follow-up here? What is your confidence that the warm water anomaly that started in 2013 and was also believed to have occurred in 2011 and 2004, is that a product of climate change?
There's a small piece of that, but it's a combination. The way I like to think about it is we have a small forcing from climate change that's always there, but then when you add natural variability, and part of the North Pacific is we've switched from a cold regime, I think, to starting a warm regime. Now when you start adding the feedbacks that are in the Arctic, the melting ice and the tundra and vegetation, we can lock in some of that extremes. So it's a combination of a little bit of global warming plus natural variability puts us in a place we've never been before. So I've been looking at some of the global warming scenarios that Julie was talking about, and they're probably too slow because the models don't have all of these interconnecting pieces.
Go ahead.
I was going to add one thing. I think it's generally thought that the blob was forced by western tropical sea surface temperatures, and they've been amazingly warm. And so it's more likely a tropical forcing, not an Arctic forcing. But one thing that my students and I have looked at is when we have warmer than normal water in that blob area, we tend to have very warm Januaries in Alaska. And some of the real peak, a lot of our peak fire seasons have occurred when that blob was very warm. But again, we only have a few cases, so it's something we're looking into.
I'll just reinforce the point that these trends are pointing in the direction of, previous warm periods. So I always like to say, I think it's Yogi Berra, deja vu all over again. If you look at in the past when the Arctic has warmed, not due to CO2, but for other reasons related to the Earth's orbit and so on, we saw these things migrating northward. We saw a decrease in the sea ice, and we see the moving of the tundra. So from my perspective as someone who studies the natural variability of the past, what's happening today is certainly all in the right trajectory of how we understand the Earth system to operate.
Hello, my name is Catalina Arevalo. I'm an environmental reporter from Spain. My question is for Julie. You said that the Western Antarctica meltdown, it will be the worst scenario for sea level rise. Could you tell a little bit more about that?
Well, these ice shelves that have been holding back parts of the West Antarctic ice sheet, particularly in the center of the West Antarctic ice sheet, these ice shelves are falling apart. In fact, in the a report of the National Academy of Sciences compilation of the International Polar Year, we pointed out that in the last decade, we've had 7 of the 11 or 12 ice shelves in the Antarctic Peninsula have all collapsed or are in the process of collapsing now. And so now we're seeing this further collapse happening, the loss of the ice shelves in central West Antarctica. And the point is, when you lose the buttress, you're getting a steeper ice cliff at the grounding line, and it just can't support itself. So it has to fall. Just again, think about that cathedral. You've taken away the buttressing, the cathedral will fall down. And what's happening is now the ice cliffs are so high that they just can do nothing but retreat. And one of the interesting complications with West Antarctica as well is that not only is the ice grounding line retreating and because of its height, it's going to get steeper because back underneath Antarctica, you're going into a deep trough. So what that means is the cliff can only get steeper and higher. So this is where the glaciologists are telling us there's no way to turn this off. And so we are committed to at least a meter, and I actually think that's a real minimum over the next, say, 5 or 6 decades. And the problem is it's not going to stop at that point. So we really need to take this quite seriously. I think the difficulty for most of us to understand it is that you know, we're all really good as humans to respond to emergencies. Something that happens in a day or two, then we can respond. But something that takes decades is very hard for us to wrap our head around. And yet these ice shelves are disappearing, the buttressing is being lost, and that has really tremendous consequences for the rate of sea level rise, which could in fact be, it could be quite rapid, and we may be underestimating it. So there's a large number of scientists in the all across the world who are working on trying to get this right. How can we get this more accurately predicted to look at both the glaciology and then the consequences of losing these ice shelves? So did that answer your question? Yes. Thank you.
Do we have additional questions from anyone?
Okay. Thank you. I would like to ask Professor Bhatt. To my knowledge, there is a very substantial snow melting in springtime. But as you said, increase of snow make it declining of greening. And also, I think in winter, looks like there is some increase of snow. I don't know about Alaska, but over Siberia, that's quite evidence. But I'm wondering why.
So it is a bit of a conundrum, because on the one hand we say that the climate's warmer, so there's less snow. But let me first say we really need more robust, long-term gridded observations of snow in the Arctic, particularly for the tundra region. At lower latitudes or south of the tundra, there are many more station data that can be used for confirmation. But I'll tell you that at Tulik Station, over the last few years, people have documented increased snow and a later green up. And more snow during the wintertime, or particularly during spring, that's our analysis suggests that, is consistent with a warmer climate because you have an accelerated hydrological cycle. So you're transporting more moisture to the Arctic, it's warmer, you can get more snow in the wintertime. So it's this very subtle thing that we really need better data to sort out exactly the timing. But I think that both of these mechanisms seem to be occurring.
Can I add to that? It's really interesting. If you go back to the last interglacial naturally warm period for the Earth, 125,000 years ago. What's really interesting is that we see both in Alaska and in Russia, Chukotka, an expansion of tree line. And so tree line advanced. And one thing that was really interesting when I worked in Russia is they have a funny little pine tree over there called Pinus pumila. And Pinus pumila looks like a little shrubby pine tree, and it only grows in deep snow. And so, and when you go into those forests, the snow, you see these pine trees, and the snow piles on top of them, they flatten out. And then when the snow melts, they pop up again. It's really kind of odd. So the only time you see Pinus pumila is when you have extremely deep snow. And yet in these previous warm periods, we see Pinus pumila going way north into what was tundra. So you see this during these warmer intervals, even though the summers are much warmer, you're getting deeper snow because of that ramped up hydrological cycle. So we can see that in these old fossil records of fossil vegetation, essentially, that really reinforce that what she's saying about what we're observing today.
Julie, you mentioned that the impacts of what are going on in our Antarctica are going to be stronger in Alaska. Could you talk a little more about that?
Yeah, it's completely counterintuitive. You know, when we think about sea level rise, we think that sea level is going to rise like it goes up in a bathtub, right? Sea level goes up and it goes up the same everywhere. Well, that's not the case. And the reason is because the Earth has a gravitational field that's not the same everywhere. So if you have mountains, you maybe have a higher gravitational pull, or if the Earth's crust is a little thinner, you have a less gravitational pull. So the gravitational pull around the Earth is very different in different places. That changes the shape of the ocean's surface. It's really hard to think about, but actually it's not perfectly round, it's kind of bumpy. So parts of the ocean surface are a few meters higher here and lower here because of the gravitational pull on this fluid ocean around the Earth. So it turns out that geophysical modelers have determined that if you remove the mass from Antarctica, because of this gravitational difference, it causes an increase in sea level in other parts, particularly in the northern hemisphere. And if you look at the maps that they have, the larger increases are actually up and down the east coast of the United States and also around the coast of Alaska. And it's from my own personal experience, I've actually I've been measuring the old shorelines around the coast of Alaska earlier in my career. And it's really interesting when I go back and compare the elevation, the height of, for example, Wainwright is sitting on the last interglacial shoreline, the village of Wainwright. And if you look at the elevation of that, it's a little bit higher than what most scientists would say what sea level was 125,000 years ago. That we think sea level may have been about 6 meters above present. Well, Kivalina is more like 8 to 10 meters above present. So there's a slight exaggeration. Now this 30 years ago, I could not figure out why there would be such a difference, because I was thinking about the Earth like a bathtub going up and down. But the geophysicists now show us that because of that gravitational pull, there is going to be some areas of the globe where the sea level is actually accentuated. So a lot of the old shorelines that many of the villages sit on today are a little bit higher than what was global sea level. And it turns out that if Antarctica melts, you get accentuated sea levels in the north, in the high latitudes. If Greenland melts, it actually has a larger impact on southern hemisphere sea level rise. It's totally counterintuitive, but it does seem to fit the geophysical models. So how much is a little more? It's a bit hard to say, but 10, 15% higher than global sea level rise might be what you expect in Alaska.
So you're saying that it would affect Wainwright and Kivalina. What you're seeing is that the water is higher along the shoreline.
Slightly higher around most of the coast of Alaska.
Okay.
The southern coast of Alaska and the Gulf, it's a bit different because of the tectonics going on there. You know, the North Pacific is sliding back underneath, so it's a little bit more difficult to predict there. But yeah, it's totally counterintuitive, but it is what we're realizing now. So it's changing our perception of the vulnerability of different coastlines. And I must say, please bear in mind, there's a complicating factor, not only sea level going up, but this means that when you have a storm, the storm waves are going to reach that much higher. And particularly with a lack of sea ice, a storm against a coastline that's not protected by the sea ice in the winter is going to be affected by more damage. And it's interesting, some of these really older shorelines associated with previous warm periods, the shorelines are gigantic because of that increased wave activity and lack of sea ice. So there's a lot we can learn from the past about what probably our future will be.
Hi, this is Yareth Rosen from Alaska Dispatch News, and I guess a question for Jim. Can you go over a little bit more about the wavy jet stream? Is this like a permanent thing that we're going to see? And how does El Nino, La Nina fit in? Can you make any predictions for next winter? Will we have more of this thing? Thanks.
Well, the thing to remember is both the wavy jet stream and the circular jet stream are natural states for the jet stream, and they vary from month to month. During the winter, they vary in the amount of from year to year that's occurring. So that's the background in the science on it. What we do, so there's a lot of chaos naturally in the mid-latitude weather, which is what makes the question of whether there's a firm impact from the Arctic harder to do. What the recent evidence does is the pattern shifts naturally from the circular to the wavy pattern, but once we set up the wavy pattern, if we have the circular pattern, the winds are really strong and there's not enough time for Arctic warming to really impact the air as it goes by. But if we have the wavy pattern, naturally it slows everything down and keeps the air over these Arctic warming places, so there's enough time for the Arctic warming to have that impact on maintaining that wavy pattern and maybe making the storms worse than they would have been if the Arctic hadn't happened. And it's not just the Arctic impacting mid-latitude weather. Mostly mid-latitude weather is just chaotic storms and waviness flipping from these patterns. But one thing we're seeing now is we have more than one physical factor impacting the weather. So the other one is certainly El Nino, and a good example of what we didn't see before that we've seen was in winter 2010, they called it Snow Armageddon, that dumped 4 feet of snow on Washington, D.C. And what happened there was you had a strong El Nino that brought all the warm, moist air across the southern U.S., but then you had a wavy jet stream that brought cold air down from the north, and when the two were occurring together, you ended up with a new extreme weather event that you never saw before. And we think we're seeing more of this interaction between what's happening in the Arctic and the timing of what's happening from El Nino and the equator, but also the randomness of the jet stream in itself. That wavy pattern not only varies in how strong it is moving north or south, but it shifts east and west. So part of the way we get the real strong storms in the eastern U.S. is it depends on what's happening in the Pacific, how this waviness lines up to get the initial conditions, and then the cold air from the Arctic can reinforce that already existing condition. So we, rather than long-term trends that we tend to look at, because there's so much chaos in the atmosphere, what we're actually seeing is more variability. We have both warmer years and colder years in the recent half decade. And the other part of the problem there is it's just really showing up since the Arctic's warming up from about 2005 onward. And so we don't have a long record to say how different it is. We can't say there's a strong effect, but we can't say there's not a strong effect because there's not enough information. But if you're thinking in terms of risk assessment, this is one of the additional surprises that we keep seeing in the Arctic, and you add all of these different pieces together, which makes the Arctic a strong indicator for global warming, because the acceleration is so much faster in the Arctic. We were talking about 2-degree global warming by 2040, but the Arctic will be 4 degrees because of all these internal features. So I like to say there's a little bit of global warming, but then it gets amplified by what's going on in the Arctic.
Let me add one thing. There's various groups of atmospheric scientists who are looking at these wavy patterns, much like you'd look at the wavy Tanana River out here. So the Tanana River goes like this, and so you can actually measure the curvature of each bend in the river. So you can actually measure the curvature of these wavy patterns, and then look at both their curvature, their arc, and then also the frequency that they happen. And so they're trying to look at now what seems to be a trend toward more waviness and these tighter curls. And so think about that Tanana River. If you can measure how that varies, we're doing kind of the same type of thing with the atmosphere to evaluate that. And so then to compare previous decades with what's happening now, the experiment will continue as we continue to measure this waviness and how persistent it becomes.
Just to clarify, so maybe in the past we had these wavy, well, I'm sure we did. We had the wavy patterns, but maybe people didn't notice because, is that the case? Or is Arctic warming causing more wavy patterns, and how much evidence is there of that?
Well, there's some thought, and you can correct me because you're the expert on this, but the idea is that if you have a gradient from the tropics to the poles, it's cold, warm here, cold here, and if you warm the Arctic more, relative to the tropics, you're flattening the gradient between the tropics and the poles because the Arctic's warming more, because of what we call polar amplification. That it may be that this change in slope has a change in the waviness, and so it's ongoing research. I think it's to test this, it's not that this waviness never happened before, but it may be that the frequency of its occurrence is increasing now. So it's a fascinating area of science to watch what's happening.
Yeah, and just to add to that, what we do see in early winter is stronger instances of both of those patterns. So it's not just we're going to waviness, but one year we'll have a really strong circular pattern, and in other years we will have more instances of the wavy pattern. And the reason for that is just the natural chaos, but the question is the extra energy that we're putting into the atmosphere from the changes in the Arctic making the whole system have more energy. So we don't just have more waviness, but we have more variability and shifts back and forth between the two patterns. So we've always had those, and 20 years ago we thought, yeah, this tight circle always keeps the cold air in the Arctic. So whether we weren't looking so much then and we're looking more now, or whether there's a change, both of those are realistic ideas.
Just how people are measuring this? It's like with a river that goes back and forth on the land. Think of the jet stream as a river of air, and you can measure the curvature of how that bends around. You can measure the arc of it, and how tight a curve it is, and so you can. So just to simplify, you've got this jet stream that instead of acting like a straight river system that's high speed, it's kind of acting more like a meandering river in the atmosphere. Does that explain? Okay.
And just to continue with the river analogy, the river doesn't necessarily stay in one place over time. It might change over 10 years or so, where in the atmosphere it can change over a month or so and flip back and forth.
Right.
But they can measure the waviness.
Sorry, to you next. Is there something similar that's happening with Antarctica and the weather in the southern hemisphere?
Well, let me see if I can answer that. Interesting that in Antarctica we have the West Antarctic ice sheet area, and the Antarctic Peninsula is warming up quite a bit. So that's why we're seeing the massive melt there. There's not quite as much warming elsewhere, but certainly the West Antarctic ice sheet is undergoing dramatic melt. And it's very interesting. You may also realize that we've had increases in sea ice around parts of Antarctica. So we're actually, the National Academy of Sciences is having a study that's going on about that conundrum, because, well, if it's global warming, why is the sea ice more extensive in Antarctica? But it actually may be, one idea is that with the melting of the ice in West Antarctica, parts of Antarctica, you're putting more fresh water out over the salt water, and it's much easier to freeze fresh water than it is salt water. That's one idea. So, and if you increase wind flow, you can actually get that open water and produce more sea ice. So there's several different ideas about this, but this is kind of what they're looking at, is in fact, it might be, as ironically as it may sound, that the warming of parts of Antarctica is actually responsible for the increase of the sea ice.
And then no associated weather changes?
Yeah, I can't comment directly on actual day-to-day weather patterns. Maybe you can comment
Yeah, a
on that?
bit. I mean, the basic idea is the Arctic is water surrounded by land, and Antarctic is land surrounded by water. And in the northern hemisphere, we have these big rocks in the flow of the jet stream, in the way Greenland is this big rock, and we have the Rocky Mountains, and we have the Ural Mountains, and so in the northern hemisphere, that's why we tend to get the waviness just naturally. In the southern hemisphere, it's all of this in both hemispheres is driven by the poles are colder than the mid-latitude. So the basic forcing is the same in both areas, but in the north we have more waviness because of the mountains. Around Antarctica, you tend to have much stronger of the just circular pattern, and the Antarctic Peninsula sticks out into the jet stream river in the Antarctica. So you see people that, oh, the peninsula is really warming and it's all tied in, where a fair amount of Antarctica doesn't have long-term real warming trends, because it's more protected living inside the jet stream down there. But then when you start adding changes in the ocean and changes in the ice flow, all of a sudden you start changing the ocean temperatures, and then that changes the north-south temperature difference that drives the jet stream down there. So again, in the past, we tended to think these things in both hemispheres were really isolated, and now we're starting to see two-way interaction because of all these special one-way feedbacks that occur both in the Arctic and in the Antarctic.
Thank you. Thank you very much for doing this. I had two questions, or one question related to two milestones this week. One, we've have NASA sort of announcing the sort of February temperature records, which sort of broke through previous temperature standards by, I think, a shocking amount. And two, we expect that they're going to declare the sea ice cover records any day now, and it's a new record low. So what, if you could sort of say what these two records are saying for us at this particular time? I mean, if you do see a message here? And B, if you could sort of speak directly to what degree the sea ice record low is a signifier on itself, or, you know, parse out whether it's a signifier or of a new shift, or just because of variability. If you could speak to that a bit.
Well, certainly we're setting new records as we warm the planet. We're even in winter. I mean, the carbon dioxide in the atmosphere kind of goes like this over time, up and down. And even in winter now, we're well above 400 parts per mil globally. So we are increasing the greenhouse gas blanket, and that dramatically increases the temperature, particularly in winter over the Arctic. And of course, now we're seeing record warming in lots of places. So the predictions for Arctic sea ice have been interesting. If you just went back 10 years ago, maybe 10 or 15 years ago, everyone thought the Arctic sea ice, the Arctic would not be ice-free until about 2100. So I figured, okay, I'm never going to see that. I'll be dead before that happens. But now, the thinning of the ice, the lack of the multi-year ice that's thicker, and you're getting much thinner, more vulnerable ice in the Arctic, it really is pointing toward a demise of the Arctic and maybe in more ice-free conditions at an earlier date. And some people have forecasted as early as 2028. Others have said maybe 2035, 2040. Well, I might actually be able to see that before I leave the Earth. And so there's, I think the changes are happening much faster than any of the earlier predictions. And you guys can comment because you're the experts, but the modelers haven't been able to get the sea ice component right in climate models. And that's why a lot of the models are kind of forecasting way out, and things are happening faster than they could predict. So do you want to comment?
You can't underestimate how big the change we saw in the warming in January and February in the Arctic. The January number was 3/4 larger than the previous record in the Arctic. So not only have we beaten the record, we beat it by an unbelievably large amount when you're thinking about how the Arctic temperatures have changed in the past. And what we see on why are we having these warmings, we have the long-term changes of global warming and CO2 and the ongoing melting of ice and snow that keeps the long-term trend going. But then in the last 2 months, we've had the connection from the mid-latitudes warming, and then that warming being carried into the Arctic. So that's the random variability added on to the long-term trend. But what makes this so startling is the warming is something that we would never have expected such a jump in 1 year, and it has to do with the whole Earth system shifting. When the northern Pacific changed back warm, it goes back and forth between cold and warm, but now when it turned warm at the same time that the Arctic is warming, you add those together and it sends us into a new temperature place that we've never seen before. And then the Arctic has all these internal amplification mechanisms that we've been talking about, the tundra change and the melting permafrost and the sea ice that amplify and are a flywheel to keep this change going. So I'm one of these people that I wrote a paper saying the ice is going to go away in 2060, and then it was less than 2 years. We said 2040 and maybe 2030, and I've been living with that one for about 5 years. But after this year, you know, that's probably out of date as well. We don't know what this winter warming is going to do. I agree that the ice loss that we have in winter, you've got to be a little careful because that ice loss is the Bering Sea and north of Norway. So that tends to be south of the Arctic Central. So that's a little different indicator, and it has to do more with what the warming going on at mid-latitudes, just random. But there's no doubt that the absolute record Arctic-wide temperatures being much greater than the previous record is probably the all-time surprise that we've seen in the Arctic. And being around in this, the ice loss in summer in 2007 was one of these surprises, and the glaciers or the ice sheet melting so quickly is another one of these surprises. And I keep getting surprised every couple years on how rapidly the art is changing in ways we were not able to anticipate how rapid things are.
I guess I'd like to add one thing and emphasize something Julie said, was that with very little multi-year sea ice, I don't see how the ice is going to grow. It's going to keep decreasing unless we have a series of amazingly cold summers that helps preserve that ice from 1 year to the next.
Yeah. So it's very difficult for anyone to see what would turn that around, that the warming is continuing, and sea level is not reversible. So
Right.
so that we have the long-term trend is certainly for a warmer world. So, yeah.
This question's for Julie. I'm not sure what the resolution of the data that you get in your quaternary geology research is, but to what extent is there an analog that we can see? Can we see sort of this level of, I don't know, year to year, how quickly the Arctic has?
Yeah, if we look at the last time we came out of the last ice age, we can see how fast sea level came up. And there was a period of time when sea level was coming up 3 or 4 meters, in a decade. And so when you're melting these massive ice sheets, it can happen really fast. So we're kind of looking at that as that's how fast these ice sheets can collapse once they start. Again, that was at a time when we had a large ice sheet over North America and over Eurasia. But still, sea level can go up quite dramatically once these things get going. So those are the best analogs we have. And the question is, how fast can we model what's happening with these present ice sheets? So the other way to look at it, if we go back to in the 20th century, okay, so say from 1900 to 2000, we had a sea level rise of about 1.1 millimeters per year. Okay, so this much a year. We're now in the last 2 decades, we've gone into a regime where sea level is now rising at 3.1 millimeters per year. Okay, so that's a tripling of the rate. And we think that's going to increase. We may be talking about centimeters per year here in the next decade or 2. Now, that doesn't sound like much, but you just take 10 centimeters, 20 centimeters over a couple of decades. And so the rate of sea level rise is accelerating, best we can see. And because of the warming, that rate will increase. Let me add, too, is that currently we think that half the sea level rise, half of what's going on is simply the warming of the ocean. So the surface waters of the ocean, when you warm them up, they actually take up a little more space because you have a little bit of expansion in the volume of the surface waters, the upper 100 meters of this water. So the surface waters of the oceans are warming up. That's actually taking up more space. It's almost so hard to almost believe on a molecular level, but you're actually expanding the surface waters, and that's actually part of the sea level rise. It's not all the glaciers. 3.1 millimeters. A year, yeah.
Just a clarification of numbers, 3.1 millimeters now, and that's tripling of what rate prior?
It was 1.2 millimeters per year. Now it's 3.2 or 3.1, 3.2 millimeters per year. And this is pretty well documented in the IPCC assessment. So those numbers come from that. And again, those are based on, tidewater measurements as well as satellite imagery and a lot of assessment by a lot of scientists to come up with those numbers. But everyone agrees the sea level rise is definitely increasing. And, as I say, we could be looking at a centimeter or more in the coming decades, which is really fast.
Thank you.
All right. Thanks, everyone. Thanks to our panelists and participants. It looks like those are all the questions we have. If anyone has follow-up questions, you can please feel free to email them to Marmy and Grimes. Her email address is on the main conference media page at assw2016.org/news/media. You can also reach the staffed press room at 907-455-2005. Today's visual aids are available for download from the press download folder. The address is on the whiteboard in the press room. And we'll have another briefing coming up at noon. It's about a newly published paper in Nature Geosciences about permafrost thaw. Thanks, everyone. See you later.
I bet you know the answer to this. I've been trying to find, when I was educated, I was told, warmer Arctic, there's more snow. I remember John Kutzbach taught me this. I cannot for the world of me find the original reference. And I talked to John Walsh, like, who's the first person who put that theory forward?
I don't know.